Here we are going to talk about other R-tree variants. So the first variant that we are going to talk about is the R-tree packing. So basically, this is a very spatial R-tree variant. It only deals with the static case. So that means if all the rectangles or all the data they are already stable, then in this case the data can be preprocessed before creating the index. And the purpose for that is to optimize the space utilization. So which means that all the nodes in the R tree are full already. So as you can see, this is by using the same dataset that we have seen before, which is the hydrography network, and this is the R-tree structure. And the R-tree packing, because the you can say hydrography network data is already static, and then we know all the data, and then we can try to maximize the space utilization. So instead of inserting the data one by one, we can first do some preprocessing. For example, in this case, this is the result from sort tile recursive packed R-tree, or it's from str packed tree, or str packed R-tree. So what it actually does is actually it will sort the data according to the XY coordinates. So as you can see, it's kind of a little bit similar to the grid structure, right? It's kind of similar to a grid structure. So it will sort the data. You will first sort the data and then see, okay, so this portion of the data, it has a certain number of the threshold. Let's just assume that, for example, here we have 1,000 entries in this region. So we scan the axis first. And then here, from this point to this point, here entirely for this column, we have 1,000 entries, and then we will just stop it and treat it as another column of data. And then here we will start the searching, and from here to here we achieve the 1,000 entries already, and then this becomes another column of data. And then starting from here to here, we have another 1,000 of data. And so for the parts that the data is very, you can say, dense. So as you can see, those columns are denser, a smaller, you can say a narrower column over here. So that means the data over here, they are a large amount of data locates in this column. So this is like you can say sort the data and then split it into tiles. So in the x direction first, and then inside this column, then we will split it again in the y direction. So which means that, for example, for that 1,000 data, then we can set that, okay, so for every 100, we will group them together in one node. So starting from the top to here, so from here, from the top over here to here, then we already have 100 data. So we will put them into one node, and then from here to here, we will we'll divide them and put them into another node, and from here to here, we will put it in the third node, and so on and so forth. And as you can see for this one, from here, and then it will the density of the data here are not so high. So in this case, it will have larger coverage in the y direction. So starting from here to here, then we have 100 entries. So they will be grouped inside into one of the node. So as you can see, for the for the portion that the data is denser, then you have, you can say, narrower or smaller tiles for those regions. So in this case, by sorting the data and then make them into tiles, then in this case, each of the node can the space utilization for each of the node can be maximized, and in this case, all the disk blocks are utilized, and then the smallest size of the tree can be achieved. And on the other hand, as you can also see that the node overlapping percentage are also reduced compared to the original R tree. So the search performance in this type of tree is also better than the traditional R tree. Okay, this is one of the variants that I'm going to introduce, and then let's move on to the final one that I'm going to introduce in this course, which is the R plus tree. So the R plus tree is actually a very spatial variant to the R tree, and you can kind of see the R plus tree as the combination between the data-driven approach and the space-driven approach. So it has some characteristics, and so the first characteristics and one of the most important characteristics to the R plus tree is that it doesn't have any node overlapping. It doesn't have any node overlapping. So if there's any node overlapping, then that means you need to when you have any query, then you need to travel to multiple paths inside the tree. Then in this case, it will take more time to execute the query. So if there's no node overlapping, then that means point queries, they can be supported by having only one single path from the root to the you can say to the leaf node. So just one single path. So the query performance for the point query can be largely improved. So then this type of you can say characteristics is achieved by having the objects to be clipped to achieve this non-overlapping goal. And then in the R plus tree, it also has the same characteristics, so the same mechanism of the R star tree, where the reinsertion can be applied if necessary. So let's take a look at this node structure over here. So as you can see, the largest node over here is the root node, that's the R, and we have the A and B indicates with the, you can say, the border dashed rectangle over here. So we have the A and B, and as you can see, one thing, the A and B, they are not overlapped together. They are not overlapped with each other. They touch with each other, but however they didn't. They are not overlapped with each other. And inside the A node, we have the X, Y, and Z nodes. And as you can see, that we have the X over here, Y over here, and Z over here. So we have these three nodes inside the A. So X, Y, Z handles different, you can say, entries. But however, the most, you can say, the most different part is not in the A node, it's actually in the B node. So let's take a look at the B node. The B node, it has the P node for the dashed line over here. So we have the P node over here, and we have the Q node over here, and we have the R node over here. So you can notice one thing, that P, Q, and R, they don't really have any node overlapping. Right? They don't have any node overlapping. So supposedly, if it's the traditional R tree, then in this case, for example, like P, the node, for example, you can say 12 and 13, they could be grouped by the Q node. And R could be overlapped with the, it can be managing the 9 and 10, and P node could be managing 11 and 8. So that but however, in this case, you can say the directory rectangle of the P and Q and also the R, they will overlap with each other. They will overlap with each other. And those node overlapping will cause some performance, you can say performance degrading, and it's not so well optimized for the point query. So, but on the other hand, here we have the R plus tree. So how exactly does the R plus tree works? the way it works is that as you can see for the Q node, this is the directory rectangle of the Q node. It actually clip the rectangle 12 into two parts. Right, the rectangle 12 actually has been clipped into one part and another part. The small portion over here, they are grouped with the node, the rectangle 13, and becomes the Q node over here. So when you search for the Q, actually it has also an address direct to the rectangle 12. It has an address direct to the rectangle 12 over here. So as you can see from the node structure over here, we have the Q indexing the 12 and also 13 rectangles. And for the P node, as you can see, it has 11, it has 8 and 12. But however, the 8 and 12, it only manages to the edge of the here, to the edge over here and here. So the 8 and 12 are also cut into two parts. Both of them are cut into two parts. So for the P node, it handles 11, 8, and 12. So as you can see, P node, it handles 8, 11, and 12. And for the R node, it handles 9 and 10 for sure. But however, it also handles this portion of the rectangle 8. This portion of the rectangle 8. So as you can see, the R includes 8, 9, and 10. So this is how the R plus tree achieved the no node overlapping characteristics, and so it's still a data-driven approach. But however, it doesn't have the problem of the other data-driven approach that the nodes are overlapped together. So the benefits of having that, like I mentioned earlier, the point query performance can be largely improved because you can just follow the single path from the root node to the leaf node and then to find the corresponding data. Okay, so let's take a look at the summary for the R plus tree. First of all, the point query performance benefits from the non-overlapping of the nodes because you can have like a single pass down the tree and then fewer nodes are visited than the traditional R tree. So the query performance for the point query is largely improved. But however, the algorithm of the R plus tree is much more complicated because instead of just splitting the nodes and grouping those entries, you need to also consider the clipping of the data. So the algorithm is more complicated. And the other more you can say critical drawback to this design is on the window query. So although it has been improved for the point query, but however the window query you could have the for example, you could have a window query over here. Let's just say like a window query over here, like in this region. So if you have a window query over here, then in this case, this window will cover with P, Q, and R. And from the P, it will have a candidate result, which is the rectangle 12, and from the Q, it will have the candidate result of 12 and 13. So as you can see, you will have the duplicates occurs for the intermediate result. So in this case, similar to the space-driven approaches, those duplicates needs to be removed before the return of the result. So this object duplication, it will increase not only increase the tree size, and also it will lead to more expensive duplication removal procedure, because you need to sort the result first, and then you need to remove those duplicates. Okay, so that's the, well, you can say some of the good thing about the R plus tree and some of the bad thing about the R plus tree. But the more importantly, I hope you guys can understand the main differences between the data-driven approach and space-driven approach, and they and how those node overlapping or larger area of the node will affect the query performance. So hopefully you can well, try to think about that aspect, and then try to think about how to you can say understand that. And through the in-class discussion, I hope I believe that you guys can have more deeper understanding about the, you can say, space access method performance behavior. Okay, finally, here is you can say a timeline of the spatial access methods. It's actually a very interesting interesting a review, and also the collection of those different spatial access methods. So as you can see, here is the timeline from the 1966 to about 1998. So this is old time actually. So there are some new trees that of course was not included in this paper. But as you can see, the B tree is over here. All right, the B binary tree is over here in the 1972, and we have the R tree over here, and then we have the packed R tree in the 1985, and R plus tree over here, R star tree over here, and yeah. So basically, here is the R tree variations and families, and we can take a look at also space filling curve is over here. And then here is the point quad tree. The point quad tree, and then space filling curve will lead to the Z ordering, which is over here. And then I believe there are some other trees that are also, the grid file is over here. Here is the grid file, and there's another important tree that we actually didn't really mention, which is the KD tree. It's the k-dimensional tree, and it has been utilized in many multi-dimensional data management. For example, sometimes people use that to use the KD tree to manage the 3D point clouds. So this is also one important spatial access method over here. And yeah, so basically that's well, this is just for your information. So it's actually quite interesting to see how they relate to each other, and then what's their relatives, and what's the, you can say, idea innovation through the whole evolution of the spatial access method. So I'm actually not sure whether there's a newer version of this type of collection. But however, if well, you are feel free to to do some search, and then see if there's any new like extension to this timeline. Okay, that will be it for everything that I prepared for this unit. So this entire unit is actually a very huge topic, and a very a spatial topic in the database management system. And but however, this type of spatial database or spatial access method is one of the critical mechanism and critical component in any GIS system. So hopefully, and actually, I don't think it's very. It's not a topic that people usually teach, and not a topic that people usually, well, you can say, explained, even if in the like graduate level course. So hopefully through the some brief introduction in this unit, you can understand some background and also some of the deeper understanding to the spatial access method. And maybe in the future, if that's your research interest, then you can try to dig into the details and try to well, invent or create a more efficient or more you can say a spatial access method that has some you can say advantage in some of the aspects. So that will be it for this unit. Let me know if you have any question.